MedVision 3D/4D is a high-throughput three-dimensional image informational model for medical professionals, a development project proposed and presented by Avatar MedVision US LLC, North Carolina, USA. This presentation is an intellectual property of Pentagram Research Center Private Limited, Hyderabad, India, to be shared by Avatar MedVision US, and it is meant solely for marketing purpose. No part of this presentation should be copied or reproduced by anyone in any form or kind for any commercial use other than our authorized personnel or agencies. This presentation is produced by me, Rajan, the founder-president of Pentagram Research Center, Hyderabad, and the technical director of Avatar MedVision US LLC. Technically supported by Mr. G. Satya, Dr. G. Ramesh Chandra, Dr. Michael P. Coyle, Ms. G. Prashanti, graphically supported by Yashasvi Vemuganti, and the commercial support by Mr. Pat Krishnan. Three-dimensional image processing is an important area of research that has numerous applications in the fields of medical imaging, seismology, geomorphology, remote sensing, and material sciences. Depending on the requirement for solving a specific problem, one has to identify various features of three-dimensional images while applying suitable algorithms. For example, the quantitative analysis of anatomical structures in MRI, CT images requires extraction of volumes and shapes of certain parts of human body. In order to do this, there is a need for detecting features such as points, lines, contours, surfaces, wireframes, textures, and skeletal forms from three-dimensional images. Detecting such superficial and volumetric features of three-dimensional images has always been a difficult task, and there is little progress made and found in literature. MRI-guided laser system allows surgeons to perform brain surgery on tumors and epileptic lesions in the brain. In the year 2011, a patient underwent frontal orbital tumor via parietal temporal window access surgery in Mexico. He was placed in a supraorbital chamber. A non-metastatic 3 by 4 centimeter granulated mass of about 12 grams was found. This particular patient had experienced right proptosis, right side diplopia, recurrent right hemisphere cephalia, and because of that, occasional nausea. Intraocular hypertension stage 2 was also detected. MRI-guided laser surgery was performed on him, and the patient did successfully well on his post-operatory period. Symptoms of gradual recovery were seen as expected. Minor post-surgery complications were noticed, but no long-term complications were found. Eventually, the patient recovered within 30 days after surgery. Subsequently, patient's health was observed to be stable. No sign of neoplastic mass growth was detected in the surroundings of the operated area according to 3 Tesla MRI performed in the following year and a half. The point to be noted here is that had there been proper 3D image processing tools made available to the radiologists and surgeons, more precise surgery could have been carried out on the patient and post-surgery complications avoided. This problem is the actual motivating factor behind the work carried out till date and more focused work deemed to be carried out in future. Let me begin my presentation with certain conceptual portraits of 2D and 4D, 3D, still and video images. By 2D still image, we mean the repeated display of a single 2D image at regular instants of time. Logical Image Processing System is a proprietary software product for processing still images. Breast cancer, that is most common in women, is known as mammary ductal carcinoma. This type of cancer has 2 forms: invasive ductal carcinoma, a malignant and abnormal proliferation of neoplastic cells in the breast tissues, a non-invasive, potentially malignant neoplasm that is still continued in the milk ducts. This is where the disease is most often found. According to the research statistics in 2004, in the United States, 55% of breast cancer diagnosis involves invasive ductal carcinoma. The sample video shown here demonstrates the use of a product logical image processing system for identifying regions in the scanned image of a patient. Note that the image consists of dense tissues at the upper part of the breast, which have concealed the calcification at various places. Here, 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 and here. But for the software, this would have gone unnoticed, leading to the false and negative opinion by the radiologists. The term 2D video refers to a sequence of different 2D digital images called frames displayed one after the other at regular instants of time. An example 2D digital video is shown on the left of the slide. By 3D still image, we mean the repeated display of a single 3D image at regular instants of time. Note that a 3D image is an ordered stack of 2D images called slices. For example, an MRI image is a volumetric data consisting of slices obtained by scanning a physical body at incremental depths predetermined by a radiologist. L3D IPS is a proprietary software product intended for processing 3D still images. Note that MedVision 3D is the medical version of L3D IPS and it will be developed by MedVision US LLC. Now, the term 3D digital video refers to a sequence of different 3D digital images called volume data, displayed one after the other at regular instants of time. Note that the processing of a sequence of three-dimensional images involves the fourth dimension of discrete time, and hence one could as well call this 4D video image processing. MedVision 4D is the radiologist version of this software product to be developed by Avatar MedVision US LLC. This presentation briefly describes some of the basic features of the prototype version of L3D IPS, an advanced 3D image processing software developed by Pentagram Research Center Private Limited, India, with an engineering perspective and which works on 3D image data like that of MRI datasets. As stated, the radiologist versions MedVision 3D and MedVision 4D of L3D IPS will be developed by MedVision US LLC. Now I am going to discuss the techniques adopted by L3D IPS for visualizing 3D images and their processing. Some of the basic features of L3D IPS are the following. The engineering version L3D IPS has been developed using Visual Studio.NET tools. Algorithms have been generated in the framework of cellular logic array processing. The software has been tested for its precision, speed, and robustness. Most of the traditional algorithms do 2.5D processing, but not 3D processing. Algorithms used in L3D IPS do 3D image processing. 3D images obtained by MR, PET, SPECT, and other scanners could be visualized. 3D images could be processed for extracting various spatial and spectral domain features. L3D IPS consists of 230 routines and it provides facility for user-driven macro generation. All extracted spatial features of a 3D image could be quantified provided it is scaled. Spatial and spectral domain fusion of two 3D images is possible using L3D IPS. And electronic surgery of a 3D medical image is a special feature of L3D IPS. 3D image volume is rendered in XNA Game Studio graphics framework. One can achieve rendering of 3D images by implementing volume rendering algorithms in the DirectX graphics framework. Apart from 3D image visualization and processing, a software component of L3D IPS can reconstruct a 3D image from a set of 2D images, or can load a 3D model using the recasting method. L3D IPS contains 230 routines. One can generate macros using these routines appropriately. The menu structure of L3D IPS is partially shown here. The term macro refers to a sequence of operations to be carried out successively on an image in order to achieve a desired effect in the given image. For instance, let us consider the image shown here. First, we obtain the histogram equalized version of this input, then its negative form. Then we apply gamma function to this negative form using the formula Cij is replaced by Aij power n divided by W power n minus 1, where W is the maximum intensity of the image, Aij is the voxel value, and Cij is its corresponding output. Each and every voxel is gamma corrected by this operator. Using this operator, one can manage intensity values of a given image to obtain better contrast. See the effects of applying this operator to the image given above. This slide shows a partial list of technical specifications of L3D IPS. Some of the major utilities of the software L3D IPS are extraction of volumetric and superficial features of certain parts of the human body. For the quantitative analysis of the anatomical structures in 3D images acquired by scanners like MRI, PET and SPECT systems. Some of the support utilities are dyadic operations between two 3D images, image rotation by 4 pi radians of solid angle, electronic surgery of 3D images, negative of 3D images, 3D histogram equalization, and object extraction, to name a few. Well, now we proceed with a brief demonstration of the software L3D-IPS. Volume visualization is a method of extracting meaningful information from datasets containing volumetric data and simulating geometric transformations of a 3D image in a Euclidean space. We make use of a two-pass raycasting-based volume rendering on a special-purpose GPU ATI Radeon MSI R5970 graphics card. This slide is self-explanatory, and it shows the principle of raycasting for 3D image visualization on a monitor. An MRI and its processed version are respectively shown in the left and right display window. Note that these two images are rotated in 4 pi radians using camera command. Volume processing is carried out by using various 3D image processing algorithms like arithmetic logical operations, geometric transformations, morphological processing, volume compression, detection of volumetric and superficial features, volume enhancement, and volume data conversion. Basically, 3D image processing refers to volume processing operations which are identical to those of 2D, with the difference that a 3D image is scanned with a 3D window, whereas in the 2D case, a 2D window, for example, of size 3 by 3 is used to scan the image. A 3D digital image is normally viewed as an array of pixel values called voxels arranged in a 3D grid of Z3 lattice. One can use any of the 256 convex polyhedrons as scanning 3D window of size 3 by 3 by 3. Some of them are shown in this slide. We make use of two paradigms in the development of various 3D image processing algorithms. 1. Cellular logic array processing, and 2. Mathematical morphology. I shall explain these two paradigms at a later stage of this presentation. In what follows, I am going to demonstrate the 7 operations listed in this slide with the help of L3D-IPS software, whose front end is shown here. First, let me access the GUI of the software L3D-IPS. Edge detection. We load a 3D image called self-racked. The image is loaded on the left side window. Now, let's perform the edge detection operation. We choose a threshold of 20 and execute. It takes some time. Now, the resulting image is shown on the right side window. In CAD/CAM parlance, this operation is used to obtain a wireframe model from a solid model. Now, skeletonization is a boundary surface removal process, something similar to onion peeling. Boundary surface removal is repeatedly carried out in various components of a 3D image until there is no boundary surface detected anywhere in the 3D image. This is a very complex operation and it takes time to process even a small 3D image. Hence, I am loading a stored image data called self-racked skell. This image is loaded on the left side window, which is the skeletonized version of the 3D image, self-racked. On the right hand side window, you see the previous edge detected version of self-racked. Now, let's load a 3D image data called bonsai tree. The image bonsai tree is loaded on the left side window. Now we process it with the morphological operations of dilation and erosion. We make use of a 3D scanning window 3 by 3 by 3 and a structure called A, and we execute now. The dilation is carried out on this bonsai tree volume data. The dilated image is shown on the right hand side. Now I'm going to operate on the bonsai tree using this erosion operation. The same 3 by 3 by 3 class A structuring element is used here to process this image. The dilated image is shown on the right hand side. Now the eroded picture is shown on the right hand side. You see the difference between these two, dilated as well as eroded pictures. The morphological operations of dilation and erosion have been carried out in a 3D image with mathematical precision and speed. Note that we have made use of the structuring element A of size 3 by 3 by 3. One can make use of any of the 256 such structuring elements for implementing morphological operations, and this innovative contribution to 3D image processing should exemplify an advanced technique for morphological processing of 3D images. Electronic surgery is a slicing operation carried out on a 3D digital image. We have implemented this dissection operation with utmost robustness and precision, strictly following the rules of geometric and machine drawing. Let us load a 3D MR image called Set Automatics. Look at this image. One would hardly recognize anything from this image. Now let's dissect it and visualize slides 10 to 30. See the dissected image. Now let's dissect the original image and visualize the slides 30 to 50. The dissected image is superimposed on the previous image. Further, we shall dissect the original image and visualize slides 50 to 70. Finally, let's dissect the original image and visualize slides 70 to 90. The dissected image is again superimposed on the previous image. The operation is shown here in a very rudimentary way. The dissection is carried out in 3 orthogonal directions only. We are working on developing algorithms for dissecting a 3D image in all possible directions based on what we call adaptive learning. Surface detection is an important operation in 3D image processing. A 3D image would consist of many 3D sub-objects inside it. For example, when the torso of a patient is subjected to MR scanning, various sub-objects like heart, lungs, esophagus, liver, kidney, and so on would be the 3D sub-objects of the MR image. There may be occasion when a surgeon or a radiologist would like to have a glance at the inside walls of these 3D sub-objects. In such cases, surface detection would be critical, and one could visualize the inside walls of various components by dissecting the surface detected image appropriately. For example, let's take the case of a 3D image of a human heart. Let's load an image called 2TATX1, which is a dissected half portion of a human heart MR image. Now we apply the morphological operation of erosion to this image. We make use of a structuring element A of size 3 by 3 by 3. Erosion 3 by 3 by 3 class and structuring element A. I'm executing this. Now, the image, the eroded picture, is shown on the right-hand side window. Now we subtract the eroded image from the original image. This means that the surface walls of various 3D objects are detected. We now load the image called TUTATEX1 surface on the left side window. Now we dissect this particular image and visualize the slides from 70 to 90. 70 to 90, I'm dissecting this surface detected image. Observe that the image is a bit dark. Now we shall enhance the intensity of this image by multiplying each voxel value by 2. I'm executing. Now we see clearly the inside walls of various sub-objects. Texture refers to repeated patterns in a particular direction. One can visualize a 3D digital image in 36 directions, namely x1, x2, x3, x4, y1, y2, y3, y4, z1, z2, z3, z4, and 24 more oblique directions. We have developed the notion of rank filters to extract textures in all 36 directions. Now let's load the 3D image once again to TUTATEX1. The image has been loaded on the left side window. We dissect this image and see the slides 70 to 90. I'm dissecting this image 70 to 90. This is the dissected image. Now we apply the Z1 rank filter. Texture Z1 rank filter. I'm executing now. Rank filter is a complex operation and hence it takes some time to compute the patterns in a desired direction. On an average, rank filters take 47 seconds to compute the patterns in the 3D digital image of size 256 by 256 by 256 when a normal PC is used for the job. Indeed, use of a high-speed computing system would reduce the computing time considerably. We have to wait now. Yes, texturization of this image has been carried out using Z1 rank filter. Observe the textured image. Each subcomponent has its own texture. The components which have Z1 texture appears smooth here, and the remaining uneven. Texture detection would play a significant role in the early detection of cancer in a set of MR imageries. Object isolation in a 3D MR image is carried out using either spatial domain techniques or spectral domain techniques. Spatial domain techniques are developed using size and shape information about different components, and spectral domain techniques use frequency distributions in the entire 3D digital image. What we show on this slide is that one can isolate 3D subobjects using simple arithmetic operations. Let's load now a 3D MR image called Memo 256. The image has been loaded now. Let us subtract 100 from each voxel. Executing. And now we see the resulting image on the right hand side window. See, the objects have been isolated. Now we multiply each voxel of the original image by 2 and observe the resulting image. The resulting image is shown on the right hand side. Now let's dissect the original image and see slides 30 to 50 and then multiply the dissected image by 2. Dissected. Now I'm going to multiply by 2. Executing. Now see the resulting image. The term monadic refers to voxel-wise operation in a 3D image. Some of the operations have already been demonstrated for isolating various components in a 3D image. Add, subtract, multiply, divide, logarithmic, power, exponential, square, absolute, gamma, highlight, threshold, negative, equalize, and a few other operations fall under the category of monadic operators. This presentation explains 5 operations for demonstration purpose. Let's load a 3D image called Gourad. Yes. Now the image Gorard has been loaded on the left hand side. Now we execute the following monadic operations: add, subtract, multiply, and gamma function. Monadic. We'll demonstrate. Let's add 20 to each voxel and observe the resulting image. And that is the picture. Now we subtract 50 from each voxel and observe the resulting image. And that is the resulting image. By subtracting 50 from each voxel, I got this picture. Now we multiply each voxel by 2 and observe the resulting image. And that is a picture obtained by multiplying each voxel by 2. And now we apply gamma function with n is equal to 2 and observe the resulting image. That is the resulting image. We applied gamma function with n is equal to 2 onto the input image, and I got the resulting image is shown on the right hand side now. The term dyadic refers to the operation of one image on another. Two 3D images could be fused in a spatial domain or in the spectral domain using arithmetic operations of addition and subtraction or logical operations of maximum and minimum. There are three windows in this application. The top left side window is for loading a 3D image, and the right hand side window is for loading another image. The window below is for displaying the result of a dyadic operation between these two images. Three dyadic operations of add, subtract, and max these are the operations which are going to be used, applied onto a particular image, 3D image. And we're going to demonstrate now the dyadic operations of add, subtract, and min. Now I'm opening up the application 2 to perform the operations dyadic add, subtract, and min. We'll load the first image to TATX 1. The first image is loaded here on the first window. Now, rendering of the component 2. I am loading now another picture to TATX 2. Now both the pictures have been loaded on this. Now we shall diagonally add, subtract and apply min operator between these two images and see the resulting images on the window given below. What I am going to do is, I am going to add these two images, and that is shown here. I am going to subtract to TATX 1 this image from this image, and that is shown here. Now I am going to operate these two images to TATX 1 and to TATX 2, find the minimum between these two. That is the resulting image by applying this min operator between these two images. You can see here, I can just further increase the size. You can see this, the difference between these two. Now let me close down this application too. This slide shows an example of carrying out electronic surgery using MedVision 3D. Now I am opening application 1 again and load an MRI image called skull. This image is an MRI picture called skull. Let us section this image from slide number 60 to slide number 120. Look at this. The input image is being sectioned. It's been sectioned now. That is the sectioned picture. Now let's subtract 20 from each voxel of the sectioned image. And that is the picture which is shown here. I'm slightly making it, zooming it in. You can see clearly the dissected picture. Let me close down application 1 now. As an extension to what we have just discussed, one can dissect a sequence of an MR 3D image data set in all possible directions and see the spatiotemporal behavior of insides with utmost clarity using MedVision 4D utilities. It is to be noted that dissection of a still MR 3D image is less cumbersome when compared to that of a sequence of MR 3D image data sets because of the variations in the physical size and temporal behavior of different components inside the live body of, say, a human being subjected to scanning. However, if the file size of the still images contained in the sequence is kept constant, while acquiring sequence of 3D image data sets, one can develop a strategy for dissection based on adaptive learning. The adaptive learning algorithms developed for this purpose would be of much use in the development of e-surgery tools for MedVision 4D. I'd like to list certain salient features of our software product L3D IPS. Concept to product made in-house. Fast algorithms for 3D skeletonization and thinning. They are original concepts. 3D morphological operations and algebra of geometric filters. Original concepts. The novel concept of electronic surgery in 36 directions. Variable thickness 3D surface detection is an original concept. 3D texture detection in 36 directions, again original concept. Spatial and spectral domain based object isolation, again it's an original concept which I've introduced in this product. The technical and commercial advantages of this package are: number one, academic application. L3D IPS1 is also called 3D IP Core because all other versions and variants would be developed based on this core. 3D IP Core has the following important applications. As I said, an academic application. 3D IP Core could be used as an academic package in almost all technical institutions. 3D IP Core could be used in technical institutions for imparting practical training to students, for attracting high-tech consultancy projects, and for testing and validating 3D image processing and pattern recognition algorithms that evolve as research outputs. The expected revenue in this segment in India alone is a minimum of $10 million US. CAD/CAM application. Pro-IE, IDS, and CATIA are the most prominent software tools which are extensively used by CAD/CAM engineers working in products design, civil structures design, 3D animation, machine design, automobile design, as well as aircraft and spacecraft design. 3D IP Core has sufficient and significant 3D image analytical tools and therefore can act as a supplement to these packages. This translates to millions of dollars in revenue. Subsurface imaging application. Drilling an oil rig is expected to cost $1 billion US as per literature survey and study. At present, the oil strike possibility is not even 2 out of 5. This means a minimum of $3 billion US has to be spent in order to get at least oil extraction from 2 rigs. In this context, 3D IP Core could be put to use by plugging in pattern recognition software modules for prospecting oil, minerals, and others. Then, the oil strike possibility would be almost 100%. This application, together with an AMR fitted with a GPR ground penetrating radar, is an ideal prospecting technique. Medical imaging application. Keeping 3D IP Core as the basis, the following software packages ought to be developed: MedVision 3D, MedVision 4D, CardioVision, NeuroVision, and OrthoVision are add-on modules to MedVision 3D. They are highly specialized software support systems meant for cardiologists, neurologists, and orthopedic doctors. Virtual surgery is a collection of programs that would enable surgeons to use them as surgical tools on stored 3D images of human body parts of patients subjected to, say, MRI scan. This slide shows the architecture of MedVision 3D to be developed. This slide shows the architecture of MedVision 4D to be developed. Now let me describe some of the uses of MedVision 3D/4D. 3D still image data sets from any scanner could be processed offline using MedVision 3D. Sequences of 3D still image data sets could be processed either online or offline using MedVision 4D. MedVision 3D/4D software could be ported to the control and signal processing electronics of various scanners like MRI, PET and SPECT systems. MedVision 3D/4D could be stored in cloud and apps could be developed for Android applications. MedVision 3D/4D could be used for telerobotic applications. As part of our market research, we have conducted a quantifiable comparative study on L3D IPS with reference to the following software. MITK, open source developed by German Cancer Research Center. 3D Slicer, an open source developed by Brigham and Women's Hospital and MIT Artificial Intelligence Laboratory. SCI Run, open source developed by Center for Integrative Biomedical Computing, University of Utah. Fiji ImageJ, open source developed by a team of people from Germany and the USA. Some of the remarks based on the quantifiable comparative study. The technology used in developing 3D image processing system, MedVision 3D, not only encompasses various numerical paradigms used for developing 3D image processing software related to medical industry, but also advocates a novel and meta-level non-numerical paradigm called cellular logic array processing. This ensures speed and precision. It is easy to comprehend that all ground-level physical understanding of science and technology involves only number-based mathematics, whereas mathematics itself is fabricated in a logical framework, and logic and as such evolves from philosophy. Cellular logic array processing is a constructive logic-based paradigm, and it simulates all numerical computations using well-formed formulas of Markov's constructive mathematical logic. Several new trends and techniques would be incorporated in the next version of the product so that online and offline analysis of fMRI data with 4D visualization and processing could be carried out and clinical decisions made with the help of an inference engine. The hardware requirements of L3D IPS, MedVision 3D or 4D. A desktop PC fitted with the AMD Athlon 264 dual-core 6000 plus processor running at speed 3.11 GHz with 2 GB RAM, 200 MB of free space on hard disk and ATI Radeon HD 5970 GPU. Dell Precision T5610 workstation with the Intel Xeon processor, options with up to 20 cores, 10 per processor, superfast memory to handle large data sets with ease with up to 128 GB of 1866 MHz memory. High performance graphics like NVIDIA Quadro and AMD Fire Pro graphics options with 3D rendering with an optional NVIDIA Tesla GPU compute card Dell ultra-wide 29-inch monitor for AMD mid-vision 3D and 4D applications would be preferred. All of this would not have been possible had there not been fundamental research carried out by a very capable team of people under the supervision of both Professor Rajan and Professor Michael Coyle. Now, I present a brief outline on the relevant research which led to the formation of 3D IP core. Motivation behind the research. Quantitative analysis of anatomical structures in MRI and CT images requires extraction of volumes and shapes of certain parts of human body. That is, anatomical features of a human body could be visualized as spatial distributions of basic geometric features like points, straight lines, curves, surfaces, textures, and skeletal. So, in order to detect superficial and volumetric features of anatomical structures, there was a need for detecting features such as points, lines, contours, surfaces, wireframes, textures, and skeletal forms from three-dimensional images. Detecting such superficial and volumetric features of three-dimensional image has always been a difficult task, and there has been little progress made in this area. This problem was the motivating factor behind the work completed, reported as research output, and used in the development of 3D IP core. So, we set our prime objective of the research to develop fast algorithms for carrying out the operations of surface detection, edge detection, skeletonization and thinning, dilation, erosion, closing, opening, and other morphological filters. And we make use of the following paradigms. Cellular logic array processing, introduced by Professor Rajan 1989 as a logical merger of Markov's normal algorithms, and Von cellular automata and mathematical morphology, introduced by George Mathrow and Jean Scherrer 1964 as an advancement of integral geometry and topology. As I mentioned previously, cellular logic array processing is a novel technique of realizing cellular automata using normal algorithms. Input image is the initial configuration of a cellular automaton, and the output image is its output configuration obtained using an updating rule defined by logical formula. Fast algorithms for processing 3D images have been developed as a part of this research, and a number of research outputs published as PhD theses and research papers published in peer-reviewed conferences and journals including IEEE, SMC, Springer, and IET. The basic morphological operations involved in extracting superficial and volumetric features are 3D erosion and 3D dilation. The shape and structure of a processed 3D image depends exclusively on the shape and structure of the structuring element used for carrying out these operations. A formal method has been developed to generate three-dimensional structuring elements of different shapes and structures. The research carried out and used in the development of L3D IPS employs geometric filters, which could be designed using the tools of an algebra called geometric algebra or G-algebra. This is also referred to as image algebra. Fast algorithms for processing 3D images have been developed as a part of this research, and a number of peer-reviewed papers published in conferences and journals including IEEE, SMC, Springer, and IET. I would like to list out some of the significant results obtained due to this research. Conceptualize and develop clap-based algorithms for detecting 3D points, 3D edges, 3D surfaces, 3D thinned forms, 3D skeletal form, 3D directional textures. Introduce morphological opening-based edge detection algorithm for detecting 3D edges. Developed a software component which can reconstruct a 3D image from a set of 2D images, or can load a 3D model, can create a square or rectangular solid cube whose size is specified by the user. developed a software component for volume rendering of 3D image using raycasting method in a GPU. Introduced an algorithm for generating 256 convex polyhedrons in a 3 by 3 by 3 cell structure. Introduced 3D geometric algebra, 3D geometric filters processing 3D images. Implemented a novel object slicing technique which can be used for sectioning 3D digital images. The technical benefits. The advanced research carried out for the past 25 years in the field of image processing and pattern recognition has led to the manifestation of logical 3D image processing system, a prototype product. Its future versions could be used in various 3D image processing applications like medical image processing, mineral exploration, archaeological excavations, and defense applications. Social benefits. Radiologists and other medical professionals alike can identify various features from 3D images for diagnostic purposes. Prediction of normal and damaged tissues or organs could be achieved in less time and with fewer false positives, necessitating additional non-invasive and invasive procedures. This technology would also be useful for researchers in analyzing the 3D structures in various fields like oncology, geology, zoology, aviation, geophysics, and protein modeling, etc. The economic benefits. Oil companies can have a priori knowledge about a site and then begin drilling with an improved chance of obtaining oil, meaning money and resources saved. In addition to medical professionals, other people like 3D film producers who make use of 3D image processing and analysis can get their jobs done more efficiently, reliably, and with reduced costs. We, the members of Avatar Medvision US LLC, wish to make the best use of our expertise in 3D technology achieved to date to develop the state-of-the-art artificial intelligence-based software systems Medvision 3D and Medvision 4D that would advance the pursuit of economic development and healthcare for the people of the United States of America and subsequently the entire world. The concluding remarks. We shall conclude the presentation with the following remarks. Medvision 3D, 4D would be a powerful tool to visualize and process 3D medical images. MRI, fMRI, MRA, and other scanned images could be visualized and processed with a high degree of reliability. Many unique and significant features which are not available in most other software packages. 3D technology used in the development is technically superior to most other available technology. Speed, precision, and reliability are far above those exhibited by most other software packages. Comprehensive package developed using in-house theoretical concepts, paradigms, and tools. Virtual surgery could be performed with the help of the software and associated hardware. A technological boon to radiologists, surgeons, physicians, and of course patients. Very high social and commercial impact is anticipated. L3D IPS has already been developed with an engineering perspective. Academic institutions show interest in this package. This forms the core for developing other versions. Medvision 3D has to be developed with medical perspective applicable to 3D still images. Medvision 4D has to be developed with medical perspective, real-time processing of sequences of 3D datasets. This could also be embedded in the specialized hardware of fMRI and similar scanners. Commercial advantages. $1 billion business is anticipated once the global market is properly identified. Every physician, radiologist, surgeon, and even a patient can afford to purchase Medvision 3D. Hospitals, academic institutions, diagnostic centers, and research centers can afford MedVision 3D/4D. Social impact. Other than high returns, a sense of satisfaction is guaranteed that some noble service has been done to humanity. The 3D technology used in developing these packages could also be used in developing software for oil exploration, landmine detection, archaeological exploration, treasure hunting, and so on. Our core competence lies in the following research areas: computer vision, pattern recognition and analysis, and modeling and simulation. On behalf of our project team and research team members, I thank those who participated in this presentation.